Applications of waves extension squared. For vacuum, the second derivative of the electric field phasor form, x component, is minus k naught squared times EXS. And we know that jk naught is equal to j omega naught square root of mu naught epsilon naught. And that comes from the fact that the k vector is omega over c, which is c is 1 over the square root of this, as we found out in previous lectures. But we want to go beyond the vacuum, so we're going to replace mu naught by magnetic material mu, and epsilon naught by the effect of epsilon, where epsilon is the usual capacitative term, and this term comes from the ohmic conductivity term in the Ampere's law, and that's the current density due to ohmic currents. So now it's a question of algebra. So jk, we got it from here, is equal to j omega square root. Now, use this, so it's mu epsilon effective. So now we just substitute in epsilon effective. Mu times this, square root of epsilon minus j sigma over mu.
Omega. Over omega.
Oh, right, omega. Okay, so now we're going to factor out the epsilon here. And so this is going to become something nice. We're going to write this as j omega square root mu into factoring out the epsilon, we get that. And then this becomes square root of 1 minus j sigma over omega epsilon. All right, so if we look at this and we assume that we have a very good conductor, so sigma is very large, we can forget about this 1 here, and we can multiply it out. So under that assumption that the sigma is very, very large, this becomes this, j omega. Now, the root epsilons are going to cancel. I don't care about the 1 anymore. So I get square root of mu times the term that's left here. This epsilon will cancel out, so we'll get mu times minus j sigma divided by omega. The whole thing is square rooted. So, Sam, does that look okay? It's very easy to make algebraic errors.
Looks okay to me. You did not miss a j or anything like that.
Okay, so let's look at what we have here. We got mu sigma over omega.
Oh,
and
in
we
fact,
have
you can,
an omega here, so we can get rid of that. So this can be simplified, and this is equal to j times square root, whole bunch of things. We got a minus j, and we got a mu, and we got a sigma, and a 1 over omega square rooted, and omega outside. So that's going to give us a something like that. Great. So what's left to do here? Well, Sam, we've got to calculate the square root of minus j.
Wow, how do you do that?
Well, I'm going to start you off with some geometry. So here we are. This is real, and this is imaginary. So where does minus j go, Sam? Where does it go?
Straight down on the
Straight
imaginary
down.
plane.
So there's minus j. Now, this angle, what is that?
Negative 90 degree?
Yeah, or minus pi over 2.
Yeah.
And that's a positive or negative angle, obviously.
There's a negative angle. You have a negative sign.
Yeah, negative angle, it's clockwise. So I'm going to ask you to calculate the square root of minus j. But I'm going to let you use a green pen because it's going to show up a lot better.
well, my work will be emphasized. Well, lucky that Google and you taught me how to do this, so now I can do this. Well, since we have the angle pi over 2, negative pi over 2, let's write down e to the negative j pi over 2 because it's a negative 90-degree rotation. Now we want to take a square root of this, so we take the square root. Negative j of that equals that. So with the square root, you multiply with a 1 over 2 exponent. So you have that.
J, don't forget the J.
Yeah, can't just throw it around.
That's a green J, by the way, not a blue one.
Yeah, sure.
Blue J, okay. There you go. Let's have some fun.
And let's plug this into the Euler's formula. Who doesn't
Right.
like the Euler's formula? It's not like it's very hard to use, right? So it's cos of negative pi over 4 plus j sine negative pi over 4.
Right, cosine
So-
of minus 45 degrees,
Mhm.
minus pi over 4.
So that's just 1 over square root of 2. And then extract out the minus
Yeah,
for the sign. So minus j, 1 over root over 2. Is this what you have in mind?
it's exactly what I have in mind. And actually, we can take this and substitute it in here carefully. So because we're going to need that later on. And I'll continue with the green writing. So it's j and multiplied by this square root of minus j, which is 1 over root 2 minus j over root 2 times square root of mu sigma omega. Okay, which is equal to, the root 2 can go inside, j times 1 is j times minus j is 1. So we get 1 plus j times square root of mu sigma omega over 2. And we're going to use that in the next video. It's a nice compact form. The text actually starts to get things a little too detailed algebraically by substituting omega as 2 pi f and canceling the 2's. So now you have frequency, but then you have to carry the pi around. I prefer to carry the 2 around. It's a lot easier. It's only 2, whereas pi is 3, so it's heavier. Anyway, this is what we're going to use in the next video to look at what happens to the waves when we substitute in for the exact wave expression. And we'll see it's something very nice and easy to work with.